Hello students. So in the last class, the mass spectrum of ethanol up to here we have finished. So I think you just go through the last exam. There is a mass spectrum of ethanol. If you have any doubt on this regarding this, you can ask. So it's also very simple one. So if you understood the mass spectrum of water or ethyl bromide, then you can easily understand this concept. And here also the fragmentation, it's very simple fragmentation. And here also we have the uh, M plus 1, there is a isotopic peak because of the oxygen. And here, after this, we have the applications of mass spectroscopy. So this is also a 4 marks question. It's a very important question. So in this chapter, almost all are the 3 to 4 marks questions. We can expect more questions, long answers, question answers here. So the application of mass spectrometry. So here, the application is very important, and in the advanced research and most of the research, the applications of the mass spectrometry is an important concept. The mass spectrometer, UV, IR, and NMR spectra, they are very important concept in the research field, and they have many more applications in the industrial field also, and in the research field also. So just go through the applications of mass spectrometry here. First one, the qualitative analysis and determination of the structure. So you know what is the difference between qualitative analysis and the quantitative analysis. So here the qualitative analysis means the identification of the compound, to identify the compound or the uh, types of compound. So we can easily go through the valid or this is one of the important application for the qualitative analysis to determination of the structure. So to determine the structure from the before example, you can easily understand this point. So the fragmentation pattern of the compound indicates, that means in the before example of ethyl bromide, the and methane, ethane. So here we have the fragmentation pattern from the spectrum of methane. So we can write the fragmentation pattern. So which indicates the relative assay with the with which the various bonds can be broken. That means which bond we can break in the fragmentation, and it gives the evidence. That means after the breaking of the bond, we can use the evidence from the spectra. So this spectra, so that means it gives the example or the best evidence for the pattern of fragmentation. So this is one of the method of identification of the compound by the fragmentation pattern. So we can give the fragmentation pattern for the compound, and it gives the evidence. That means spectrum gives the evidence. And then the relative stability of the fragments, that means after the fragmentation, the if they are stable, that means from the metastable state or other concept, you can understand. If they are very unstable, means we will get the metastable state or metastable peak. So which fragment which gives the metastable peak or the metastable spectrum means it is unstable, or if it gives the normal peak means we can easily say it has a stable ionic fragmentation. So on the basis of this also we can say the stability of the fragments of a group of atoms here, atom in the molecules. And then the mass spectrum becomes a fingerprint for each compound. That means each compound have their own fingerprinting fragmentation. For example, carbonyl groups, they have their own fingerprinting uh, pattern of fragmentation, and then nitrile groups and nitrogen oxide groups and oxygen groups. So ether groups, they have their own the fragmentation pattern, and in the case of alcohol also they have their own fragmentation pattern. So this is fingerprinting. It means it is particularly for their substituted compound or functional groups. So we can easily say which compound or which functional group they have. For example, they have the carbonyl group. So we have the example in next slide. So or it is a ether functional group or any other oxygen or OH group they have, we can easily say by their fingerprinting fragmentation. So here, next one is the molecular mass is one of the important parameter. That means in the mass spectrum of ethanol, we can say the base peak is 31, okay, and then molecular ion peak is 46. So here we can say the molecular ion peak. That means the given molecule with the molecular ion peak. That means the molecular mass of the given compound. If you want to identify the molecular mass of a compound, then you can easily introduce the compound into the mass spectrum, and then you will get the molecular mass or molecular mass peak. So from that you can easily identify the molecular mass of the compound. So this is also very important application. And then the structure of the molecule can be predicted. So here we are predicting the structure of molecule by the fragmentation pattern. That means here the fragmentation pattern which gives the idea about the molecule. That means structure of the molecule. So here, this is the example. This is the best example here. So their fragmentation, after fragmentation of OH group or the formation of 31 M by E ratio of 31, that is the OH. So that it gives the, or it identify the structure of the molecule on the basis of their fragmentation. So this is all about the qualitative analysis. That is to identify the structure, to identify the molecular mass, to identify the compound, we can easily go through the mass spectrometer. And then to determination of the molecular mass, this already we discussed, okay. And the example you can easily understand. That means the reliable tool for molecular mass determination accurately. That means it gives the accurate molecular mass. That fragment, sorry, the molecular ion peak, which gives the accurate molecular mass of the compound. Then molecular mass of the compound is directly obtained from the M by E value. So here we are discussing the mass spectra on the basis of M by E value. That means mass by charge ratio, which gives the, which is basic principle is the molecular mass. So we can easily identify the molecular mass of a peak. That means from the peak, molecular ion peak, which gives the molecular mass of a compound. And then molecular ion peak is absent, then the molecular mass can be reduced from the steady. That means if the molecular ion peak is absent, then the molecular mass can be reduced from the study of fragment ions. That means if we don't have any molecular mass peak, means we can easily identify the fragmentation ions, and then after the study of fragmentation ion, we can produce the, or we can use the molecular ion peak. Here the unstable molecular ion peak. It may be possible the molecular ion peak may be absent in the case they have the unstable molecular ion. If the molecular ion is unstable, so it may not give any ion molecular ion peak. In that condition, we can identify the molecular mass by the study of fragmentation. This is also very simple one. And then determination of molecular formula. So here the molecular formula of the compound can be determined. The molecular mass is different, molecular formula is different. Here we are discussing of the third application is to identify the molecular formula. To identify the molecular formula, we are using different patterns, patterns of fragmentation and isotopic peaks and many other things. And mainly here, uh, the isotopic peak, the application of isotopic peak we are discussing here. That means normally M+1 and M+2 peaks are recalculated. That means the intensity, the percentage of intensity. So the percentage of intensity peaks, the intensity peaks percentage is directly proportional with the abundance of the isotopes. So we are discussed here in the case of bromine, this is the best example. Here we have the equal length of isotopic peak. So in the picture you can see that means they have the equal. That means in the 100 molecule of bromine, this is an example of bromine isotopic peak. So in the case of 100 molecule of bromine, 50% is bromine 79 and another 50% is bromine 81. That means they give equal abundance. So if they have the equal abundance means their isotopic peak have the intensity of equal peak. So in the picture you can easily understand. So this is what we discuss in this point. That means determination of molecular formula. That means from the isotopic peak we can easily understand the or we can easily identify the compound. For example, in a compound, we have a 50-50% of isotopic peak abundance or intensity. That means it is a bromine because bromine normally present in 50-50% of abundance. If the isotopic peak is 32 and 75%, that means one is 75% of another uh, one peak height is 75%, another one peak is 25% means it is other than chlorine. We can easily say. That means on the basis of their isotopic peak, we can easily identify. We have an example. In this example, you can easily identify. Let us consider the mass spectra data of an unknown compound. This is unknown compound. We don't know the compound, which compound we have. So the molecular ion peak is not base peak. That means its molecular ion peak is not base peak. In the chart you can easily identify. So here the this is the molecular ion peak. Okay, this is molecular ion peak and this is base peak. And then what is this 100 and what is this 24? So here the intensity of length. So in the previous example we have the chart or spectrum like this. That means someone is base peak and then they have the structure diagram here in the last before examples. But here they given values. That means the base peak 100 means this is 100%. That means the with the highest intensity, the longest peak length. So this is 100%. And then the molecular ion peak is 24. So they are comparing here as I explained the principle in the 24 means it is that means base peak is 100% compared to this intensity of base peak. It have only 20% of 24% of intensity compared to its base peak. So it is 24% means this much. So like this they gave the value. So m by e ratio of 27. That means the fragmentation and all other are the fragmentation after the this is molecular ion peak means these two are the isotopic peak. Why this is two are these two are isotopic peak? Because the molecular ion peak is the highest molecular mass. It must have the highest. But after that we have a peak means there is the peak of isotopes. So this already I explained in the last slides last class. So these two are the isotopic peak. So these two are the isotopic peak. This is the molecular peak. Okay, now we can identify the compound like this. So we have the calculation. Therefore the intensity of the isotopic peak, that is the m by e ratio of 79 and 80, calculate at the as the percentage of the molecular ion peak. I said here they calculated here this all the values are calculated on the basis of or they are compared with the base peak intensity and then they compare with the intensity of other fragmentation or molecular ion. So here they are comparing with the base peak. So then we will get this value. But while calculating the isotopic peak, we are comparing this base peak with the isotope. That means we are comparing this 24% of isotope peak with the 79 and 80. That means with the base peak, sorry, molecular ion peak with the isotopic peak. So in that, the calculation is very easy here. The percentage calculation. That means we are comparing for the 24 is very simple one. For the 24, it is 24. That means the molecular ion peak have the 24 value and its intensity is 24. Then in 100 it is how much? So this is a cross multiplication like this. We will get 100 here. This is a 100. Okay, and then In the 79, if they have the 79 means the M by E ratio is 79. In that cases, what happens? The 0.8 in the 24 intensity of molecular ion peak, 24 molecular ion peak. So 0.8 is the intensity. Then what is the percentage, or in the 100 it's how much? So this is a very simple calculation like this they are calculated, and we will get the 3.3. Same in the case of 80 M by E ratio of 80. So on the basis of this we can easily identify the intensity in percentage. So this is the percentage, and we will get the value of 100, 3.3 and 3.3. So these three are the percentage of isotopic peak compared to its molecular ion peak. And then the relative abundance of M plus 1, that is M plus 1 peak, indicates the number of carbon atoms. So here the number of carbon atoms, we can calculate the relative abundance. The number of carbon atom is equal to, so this is the formula, so we have to by add the relative abundance of M plus 1 peak divided by 1.1. That means what is this 1.1? This 1.1 is the relative abundance of carbon 13. So we have carbon 12. So this also we are discussed carbon 12 and carbon 13. Carbon 12 have almost 98.9 percentage of abundance, and carbon 13 have only 1.1 percentage of abundance. So on the basis of this we are calculating only the isotopic peak relative abundance of isotopic peak. So the isotopic peak abundance is 1.1, so we are dividing here. So in the case of 79, that is carbon 12 plus 1, there is carbon 13. So M plus 1, that is 78 is the carbon 12 with the molecular mass, and 79 because of carbon M plus 1, that is M plus 1, this is M 78 and M plus 1 is 79. So here 79, that means it is percentage of intensity is 3.3, and then it is divided by 1.1, then it gives the value of 3. That means we can say there is a 3 carbon atom. So carbon 13, so here carbon 13 is responsible for M plus 1 peak. So its natural abundance is 1.1. So for M plus 1 we can say the abundance is 1.1. So we can say after this calculation it may have 3 carbon, and then M plus 2 peak has high intensity of 33.3, and then here from the 80, so here 80 M by E ratio of 80, it have the percentage of intensity, that is 33.3. Here the 33.3 is the percentage of abundance of 80. That means if it have the 50% of abundance means isotopic peak is 50% of abundance means it is bromine, we can easily say. And then the 33, that is M plus 2 peak is 33. M plus 2 peak is 33. Here the M plus 1 we can expect, so it may be because of the carbon or a hydrogen, we can say. And if it is have the M plus 2 peak isotopic peak, then we can say it may be a sulfur and oxygen. That means in the case of sulfur and oxygen they have the M plus 2 isotope. That means normally it have the sulfur have 32 and 34, they are the molecular mass, and in the case of oxygen it have 16 and 18, so molecular mass. So we can expect these two with the chlorine. Chlorine also 35 and 37, two are the isotopic peaks or isotopes of chlorine is 35 and 37. That means M plus 2 isotopic peak we can expect. But here the percentage of abundance, on the basis of percentage of abundance we can easily rule out here oxygen and sulfur, because their percentage of abundance in the nature is very negligible. It is not about the 33%. From the given data we can say it is about 33% of abundance. So in 100 we can expect 33%. So it matches or is almost similar to the value of abundance of chlorine. So in the case of chlorine, chlorine 37 normally present in 32% in abundance of nature. So we can compare these two. So we got the 33.3% of intensity by the spectra, and 32.5% is the natural abundance of chlorine. So we can compare these two and we can neglect or we can reject the sulfur and oxygen isotope P, isotope concept. So here the value of 33.3 intensity due to the chlorine who have the natural abundance of 32.5. So on the basis of this, we can easily identify the carbon, number of carbon, and then we are identified the other any other compound functional group that is a chlorine we are identified. And then to know the compound which contains the three carbon atoms. So from this before calculation, we can calculate the number of carbon. We have the three number of carbon, and then after the second isotopic peak, we identify the chlorine atom. Okay, only one chlorine atom we can expect here. So we are identified these two, and then totally the molecular mass is 78. So 78 is the molecular mass. The total mass of three carbon atom, one chlorine atom. That means from the before calculation, we identified three carbon atom and one chlorine atom. Their total um, molecular mass is 71. So after adding these four molecules, molecular mass, we will get the value of 71. Then in the 78, if we are minus 71 means it will give 7. That means other 7 hydrogen we can expect here. So according to this rule, that means nitrogen rule, the nitrogen rule, according to the nitrogen rule, number of nitrogen is here we can reject, and then we have only the one option, that's hydrogen. So then we can give the molecular formula, that is C6 here. The C3 has 7 and chlorine, and on the basis of these calculations of isotopic peak, we are identified the number of chlorine, and then on the basis of M plus 2 isotopic peak, we are identified the chlorine as another molecule, and then the molecular mass, we know the molecular mass, and then total mass of identified atom. Then we can easily say the given compound is C3 has 7 Cl. So like this we can predict the structure here. And then after determining the molecular formula, the structure of the compound is established. So this is the steps we are involving here. And then we have to identify the base peak 43. That means M dot plus 35. After the that means base peak have the highest intensity. So this molecular mass and the base peak, they have the difference of 35. That means here the base peak, molecular mass of the base peak, it is 43. So after the addition of 35 to this base peak, we will get the molecular ion peak. So that means the molecular ion peak and base peak have the difference of 35. And why this base peak is very important? It has the highest intensity. That means the fragmentation of 43 is highly stable in this compound. So that's we can expect here. So this base peak is very important because of this reason. And from this we can say the molecular ion peak and the base peak have the difference of 35. And this indicates that the Cl, that is chlorine, readily breaks here. The chlorine readily breaks away from the molecule, giving C3H7. So after the removal of chlorine, the compound, the remaining compound is C3H7 as a propyl group. That means propyl group. So here we can calculate the molecular mass of C3H7. So C3H7 have 12 into 3 and 36 plus 7, that is 43. That means it have the molecular formula of That means this fragmentation of the molecular formula of 43. So this is highly abundant. So it have the highest intensity. So it is the base peak. So from this fragmentation, we can easily say 43. Why we get the base peak 43 is because the fragmentation of C3H7 is common in the case of this mass spectrum, and it is difficult to decide whether it is N propyl or isopropyl. So the compound, the given compound is N propyl, or N propyl means a straight line, a straight chain, or it is a branched one. So that is isopropyl, because both of them can give the similar peaks. So here the peaks of the mass spectrum is not changes with the iso chain and uh, chain compound and straight line compound. So we can't say from this information we can't say it is a N propyl or isopropyl. This is solved by the photon NMR spectrum, and in that condition we can use the photon NMR condition. And if the molecular ion peak itself is a base peak, so here the base peak is the molecular ion peak. The intensities of isotopic peak are directly obtained from the mass spectrum. So here, if we have the base peak and isotopic peak are same, then the 100% is the base peak or molecular ion peak. Then we will get the spectrum isotopic peak percentage of percentage we can easily identify. So there is no need of calculation this one. Okay, and then if so, in some cases it undergoes McLaughlin rearrangement. It is one of the fingerprinting equation here or rearrangement here. Ion peak gives an important clue in the determination of molecular formula of the compound. So it is very important. So McLaughlin rearrangement. So it is also very important here. And it is a fingerprinting rearrangement in the case of mass spectrum, and it's easy one. Okay, why it is fingerprinting one and it is important one, you can easily understand here. Here, this is the McLaughlin rearrangement, and it has some condition. So what is the condition here? This involves beta cleavage of bond. So first point is they have the beta cleavage of bond. Okay, this is the carbon in the case of carbonyl compound. Okay, the first thing they have the carbon here, and then they have alpha beta gamma. If they have the alpha beta gamma carbon, is the second condition for the fingerprinting region. Second condition, and then third one, in the gamma position, if they have the hydrogen, gamma hydrogen, if they have the gamma hydrogen, then it undergo McLaughlin rearrangement. So these three conditions which obeys means we can easily say it undergo McLaughlin rearrangement means they must have carbonyl group, and then alpha beta gamma carbon, and then gamma hydrogen. These three conditions it must obey. So from this we can easily identify the position of three carbon atom in a molecule. So this is the, and one more thing, of if they obey this all the condition, then it undergo McLaughlin rearrangement, and then in the McLaughlin rearrangement they undergo alpha beta, it involves, or beta cleavage. So here the beta bond is cleavage is here, or the alpha beta, in between the alpha beta carbon the breakage of a bond takes place. So here, okay, and this is what we call the McLaughlin rearrangement. From this example, you can easily understand. So this is the compound we have the molecular ion. Okay, and here we have the carbonyl group. Yes, first condition is obeyed, and then it have alpha, beta, and gamma carbon. So the second condition also obeyed here, and then third condition they must have the alpha hydrogen. This is what we call alpha hydrogen. So this is also obeyed, and then it undergo the alpha beta cleavage, and it rearranges. Which one rearranges here? Here the carbon of alpha hydrogen it rearranges, and here this is what we call the rearrangement of McLaughlin rearrangement. And like this we will get the compound, the molecular radical ion. So we can expect this one, and neutral molecule, and then we will get the another neutral molecule like this. And this rearrangement take place in aldehyde, ketone, amines, and unsaturated compound. So the first condition, as I said, aldehyde have the carbon double bond, oxygen, that means carbonyl group. Ketone also have the carbonyl group, and in the case of amides also, so correction here, amides, they are also have the carbon double bond. So this all compound have the carbonyl group, then we can expect this type of rearrangement. And we have the another example here. Okay, here also they have the ketone example. Here we have the carbonyl compound, and then alpha, beta, gamma carbon, and we have the gamma hydrogen. Then here also the rearrangement takes place. So here this hydrogen, gamma hydrogen rearrangement takes place, and then the break of alpha beta carbon bond, it breaks here like this, and then we can expect the molecular radical ion peak. Okay, and then the neutral compound. So this is the another fingerprinting. This is one example for fingerprinting rearrangement technique. So to identify the structure of a compound, and then next application, the detection of isotopes and then their relative abundance. So this we are already discussed here. It's very simple one. The presence of isotopes. We can identify the presence of isotopes by the m plus 1 and m plus 2 in the before example we are identified. The relative abundance also we are calculated for carbon here. We are already calculated here by the formula. And then for the relative abundance of neutral isotope, that determine the at masses, that means two more larger than the parent ion. If they have the peaks larger than the parental peak, then we can easily identify. So here we can calculate where carbon, hydrogen, oxygen, and nitrogen, if they have the if they have isotopic peak, then we can identify. Here the carbon, hydrogen, oxygen, and nitrogen, they have the respective of their isotopic peak, then we can identify. So here we have the formula to identify the relative abundance of isotopic peak. So here Z plus 1 divided by Z into 100 is equal to 0.015 into X plus 1.11 W plus 0.37Y plus 0.037 Z. So this is the formula. Here, what is W, X, Y, Z? So here, W means number of carbon atom, and then H, X for H, number of hydrogen atom, Y for oxygen atom, and Z for nitrogen atom respectively. So their number here we can write, we have to write, and then the compound we can write like this. That means CW, HX, OZ, NY, where Z is the mass of the non-isotopic peak. So where Z is the mass of non-isotopic peak, the non-isotopic peak with the mass there, molecular mass we have to write. So on the base of this, Z plus 1 or Z plus 2 are the masses of the isotopic peak at a 1 or 2 units more than the parent ion. So Z plus 1 or Z plus 2 are the masses of isotopic peak. So here as here we can say this is Z, okay, and this is Z plus 1 here it is the Z plus 2 isotopic peak. So this is the example. So on the basis of this we can calculate the abundance here, and then detection of impurity. So the next application is detection of impurity. The best method to detect the impurity, the detection impurities in part per million is only possible if their structure differ considerably from those of the major compound. That means if they have the structural difference, then we can identify the impurities, but it is part per million only. So in the part per million only we can identify. And if the molecular mass of the impurities is much larger than the major component, the detection of is very easy. So here the compound with the larger than the major compound, the impurity is larger than the major compound, then we can easily identify here. And then determination of latent heat of the vaporized of liquids. So here, according to the Celsius, so here equations, the log P is equal to minus delta H by RT plus constant. So here delta H value can be calculated if the value of P at a given temperature, that means pressure at a given temperature is known. If we have the pressure at a given temperature we know means we can easily identify the delta H value can be calculated. Okay, the height of the molecular ion peak in the mass spectrum of the liquid whose delta H value is to measure is directly proportional to the saturated vapor pressure of the given temperature. That means delta H measure is directly proportional to the saturated vapor pressure. So here the delta H and they are related with the vapor pressure. From this relation, we can easily identify the value of delta H. And then the value of pressure are determined from the height of the molecular ion peak. It means on the basis of height of the molecular ion peak, the pressure of the ion pressure value can be calculated, and then the value is then obtained from the slope of a flow, that is means a log p against 1 by t on the slope of log p against 1 by t we can easily calculate the value here. And this is about the determination of latent heat. You don't have any calculation, just go through the formula and you have to explain what is delta H and then how they are related with the pressure and temperature. This you have to explain here. And then the last for application, there is a mass spectrometer can be used to separate the isotope of element. So we know the isotopic peak, so we can easily separate the isotopes and we can identify if they are separated. Here this is another application. And then mass spectrometry is used in the kinetic and mechanistic study of chemicals reaction. So in the chemical reaction it gives the pattern formation and it gives the evidence for the pattern, so we can easily identify the mechanism and we can give the evidence for their mechanism of a chemical reaction. And then mass spectrometer is used to determine the ionization potential of the atoms or molecules and to determine the bond strength. So bond strength, that means stability of the compound. So we can easily identify by metastable state. So on the basis of this, we can easily give the ionization potential. That means the potential of the ionization we can give here. And last application, the mass spectrometry is used to trace the analysis in the characterization of petroleum products. So in the petroleum product, to identify the or to characterize the compound, we can go through the mass spectrometer, and this is also one very important application here. So here I finished my syllabus here. That means mass spectrometry is the last chapter I have to finish. So yeah, I finished here. So if you have any doubt, you can ask in the classroom. That means we have the offline classes also, so you can ask. And in the offline classes, I will go through the revision. So thank you.